Thanks. So hi everyone, this is Chuan. I'm very happy to share our work on 3PR last year. That is generating diverse and natural 3D human motions from text. Okay, so basically this task is to trying to generate 3D human motions from the textual descriptions. As we know, like language vision task currently is something hot. So okay. So firstly, I'd like to have a very brief self-introduction. So my name is Chuan Guo, and I'm currently a fourth-year PhD student at the EC department, University of Alberta in Canada. And my research interests are including 3D human motion, behavior, and video modeling and understanding. We had a few works published on CPR, ECCV, and most of them are about human body and motion, like action to video, that is to try to animate the 2D human image with action category in a 3D environment. And today we want to focus on this text to motion work. And also we have published a few data sets. If you're interested, you can use them. Like the first one is the Human Act 12. So that is the 3D human motion data set with action category annotations. Like, for example, this is walk, this is running, this is jump up, this is warm up, something like that. And the second one is human ML3D. So that is the 3D human motion data set with textual description. So given a 3D human motion, so we have the textual annotation of like what this person doing, like he's dancing and turning left, turning right, jump up, something like this. So I also hung the webpage of our the work we want to talk about today. So the code and model and other related resources, they are accessible in this QR link. So okay, so let's back to our topic today. So when we talk about text to motion, what we are doing now is if you provide me a text description, and then we aim to generate a diverse set of and also natural 3D human motions where the context of the human motion, they align with the given textual description. For example, given this textual description, like a person sits down and crosses their legs before getting up. So these are the examples of like the generating results from our model. So we can say the character they try to performing this textual description in different ways and also in different with different duration. There are a few existing works like trying to approach this problem before our task. And for example, like this, like language to pose in 2019, but most of them, they fail in several aspects. So the first one, they either use fixed motionless, like they say whatever the texture description you give me, and then I just try to generate motions with like 100 frames or 200 frames because because we know like in sequence modeling, it's sometimes it's hard to model the sequence with variableness. But as we say, the motions, they should have different lengths. Like given different descriptions, they should have different lengths. Or like even you give me the same description, they could also possibly have different lengths, right? Like the person is walking forward and turning left. So this can be a fast process or slow process. So the motion length, they should be something like a distribution is like a variable thing instead of like fixed thing. This is first one. And second one is existing works, they usually model this problem as a one-to-one mapping. That means they usually like given one text description, they use this like they try to regress or like to predict the output pose sequence. And given one text description, they try to predict one pose sequence. But we know that's also not quite true in real because we say, given one textual description, the character can perform this like text description in many ways. For example, like a person standing on one leg, maybe the person can standing on left leg or right leg. So there are multiple ways to do that. So there are some stochasticity here. And the third one is existing works, they usually use poses as the unit of motion. That means, as we say, if you want to generate a motion sequence with 10 seconds, and usually that involves the generation of 200 human poses. If you try to just directly generate human poses, then that means you need to model a sequence of 300, and that's usually quite long, like for like a sequential model to do that. So this can be a long process, like long sequence, and also there contains some redundancy between consecutive poses, because we know like for the current pose and next pose, actually there's not much difference here. So there are many similarity between two poses, like close to poses. So to address these problems, and we propose a two-stage method here. So the first one called text-to-name sampling. That is, given you, at the first step, you give me a text description, and then I try to approximate a distribution of the target motionless. For example, if you give me like a person jump up and down and sit on a chair, so probably the length, so the target length should have a distribution, like probability distribution. And if we have that distribution, and during generation, we can just sample a value from that distribution with the probability, we say, and that will be a meaningful motion length according to the text description, instead of something fixed or like a random length. And at the second stage, if we already have the length, like the target motion length, and then our goal is try to generate motions according to the text description and the target length. So here we alternatively try to generate the motion snippet codes instead of poses. As actually this is a quite straightforward idea. That is, instead of generate, so we have to train an autoencoder using the convolutional network. And so we say, as we said, this is a autoencoder. This is the convolutional autoencoder. So at the middle stage, we can have the latent code. So that's pretty much the compression of the input pose sequence, right? So this in our work we call this motion snippet code, and this can be more informative, and also it is much shorter, so it would be easier to model. So during generation, we try to generate the snippet code and then decode the snippet codes back to pose sequence instead of directly generate the pose sequence here. And also for the generative framework, we use the temporal variational autoencoder plus like local word attention and plus some positional encoding to encode the time step. So let's look at the first stage. So the text-to-length, as we said, we want to get a distribution of the length, the target length given a text description. How should we do that? This is actually a straightforward idea. So we have encoder, and this encoder can be anything. That can be a recurrent neural network, a transformer, or whatever. But what they should do is, if you feed the textual description into this encoder, and then this encoder should give you a distribution on the discrete number. It's pretty much like a multi-class classification. So it's like we have 40. Like if the target is range from 1 to 40, then it's like 40 classes classification, and then during training we just try to maximize the likelihood, negative log likelihood of the target distribution, right? And during inference, or during generation, we can just sample a value from this distribution with the probability, because as we say, these are pretty much the discrete number, like 1, 2, 3, 4, 5. These are the lengths, and also as well the probability of each length. And then we can just sample from this distribution according to multinomial sampling or discrete sampling, and then we can get a value. Then we can use this value to try to generate the motions according to the text description. Like by doing this way, we can have different lengths even though you are input the same description, and also that makes sense in real world, right? So that's for our first stage. And for our second stage, we call this text to motion. So that's like, we don't care because we have addressed the next thing, the motion next thing. And now we just care about how we could generate motions according to the text. As we said before, we first train an autoencoder, motion autoencoder, so that will encodes the post sequence into a sequence of snippet codes or like latent codes. And in our work, this latent code is 4 times shorter than the post sequence, and also it's more informative. And for the second stage, that is for the core part of the generation part. So we say, okay, this can be a little bit more complicated, but this is pretty much a conditional and temporal variational encoder. So the left part, this part, is basically the text encoder. If you give me the text description here, and we can have the words, and also we have the position of speech, like if this word is an action or like something like a loan or something. And for the text encoder, in our work, we just simply use the bidirectional GRU here, and we can have the sentence feature at the last time step, and also the word feature at each time step. So we use this sentence feature to initialize 3 recurrent networks. So these are also 3 recurrent networks. And if we just look at one single step, we could find that. So this is pretty much the way at each single step. So firstly, we can just focus on this upper 2 branches. So this one is pretty much the encoder of the way, as we say. And so the encoder of the way, so the input of the encoder, the way encoder is the word feature obtained through the word features obtained here. And also this is a snippet code at current time step, and also the snippet code at previous time step. And that will generate, try to generate a distribution here. And from that distribution, we will sample a noise vector, and together with the previous snippet code and the word feature, and then we try to reconstruct the snippet code at current step, the CST hot. So it's pretty much, we try to reconstruct this one. So we say this part is exactly a single variational encoder, but the difference is that we plug this variational encoder into a recurrent network structure. But as we say, usually in variational encoder, we would enforce the latent normal distribution to be close to a prior distribution, for example, like a standard normal distribution. But in our work, we do not use this like fixed standard normal distribution. Instead, we try to learn another prior distribution network, that is this one. So this we call this the prior network. The prior network is pretty much the same after the encoder, but the only difference is that the input of the encoder it contains the current snippet code. But for the prior network, it do not have that. So the input will be a word feature and also the previous time step, the snippet code. So, and during training, we have to enforce these 2 distributions to be as close as possible. So, so in inference, if this is quite like something combined together, and during generation, how could we approach the whole to make it work, to make the pipeline work? So firstly, we have this textual description, and then we would input that to the text length in as we talked in our first stage, and then we can have the approximated distribution of the target length, and we will sample a length from that distribution, for example, 35. That is exactly the target snippet code, number of snippet codes we want to generate according to this textual description. And then we will feed this through the text encoder. That's pretty much this part. Not pretty much, but like literally this part. Okay, and then we would get rid of this part because we want to generate the sleepy code one by one, like we want to generate current sleepy code from the previous one and the next one from current one, so recursively, right? So we do not have the sleepy code at current step as input. So we have to get rid of this part and just use the prior network to generate the normal distribution, because we have enforced this distribution to be close to this distribution. So we can alternatively try to sample from this distribution, and then with the concat, the sample noise vector, to feed it to the decoder, this decoder, right? And so if we recursively, like we're doing this recursively t times, we can have t sleepy codes, and then we can decode this back to the post sequence like this. So that's how we try to generate the motions according to the textual description. So this is pretty much our approach framework. Okay. So okay, there's another practical problem to do with this. Like as we say, before our work, so there's no such a big data set doing this task. Usually there's only one, but that's relatively small. So in our work, we annotated a large, so far also it's the largest and also the most diverse data set called human ML3D. So there are around 15,000 human motions in this data set. And for each motion, it comes with 3 captions. So let's say we have around 45,000 textual descriptions. And during training, like in our work, we also try to mirror the motion. For example, like mirror the left to the right part and the right part to the left part. And we can just change some keywords in the description accordingly, like left hand, change it to right hand. Like basically it's just left to right, right to left, and clockwise to counterclockwise. There's not many words we need to replace. And also this is a comparison between our collected data set with the second largest data set. And also it's around, so the FPS is the frame per second is 20, and the total duration is around, like after mirroring, the total duration is around 60 hours. And that's the average duration is 7 seconds per motion, and average sequence length is around 12 words for per description. So here we give an example of our data set. Okay, so these are basically the data set and the approaches. And here I want to show you a bunch of results from our method. So here I want first, so this is a given textual description, like a person is running from side to side. And here we give 2 generate the results from our model. So these 2 are generate the results. And this one, the right-hand one is the real motion, the ground truth motion for reference. Okay, so now we can just go to some funny part. Also, like our model can cope with some let's say real actions like swimming or like crawling. We know it's not perfect because we say the hand sometimes can penetrate the floor. Yeah, but overall it looks reasonable. I say it's not perfect but reasonable. Or like push up. Or like karate kicks, karate or karate, I'm not sure. And also like get on all fours and crawling around So basically what you need, all you need is just give us your text description, and then you don't need to do anything, just run the model and can give this result. And also like standing on one leg and spinning it. So we can say our generated results, it can stand on left leg or right leg. So that shows the diversity here. Or like walking and sit on a chair, sit down in a chair. Or like slowly walk forward and return backwards. And also we can also notice there are several ways to return backwards, right? It can turn and return backwards, or you just like step back. Or here is some examples when confronting long descriptions, not that long, but it's comparably longer than before. Or like pick something up with both hands and move it to the sides and places it back down. Okay, so here I want to note sometimes it still fail in some sophisticated matters. So for example, the hand motions is sometimes is always some like sophisticated thing. So it's still not easy to do that. And this is like a figure rise from the lying position and walks in the counterclockwise circle and then lie back down the ground. So we can watch it again. And this is the last one, like someone is walking forward and holding a handrail very carefully as if they are afraid of falling. So we can say it's quite different from the other walks we showed before. It's something like carefully walk here, slowly and carefully. Yeah, so yeah, it's quite a short presentation, and okay.
All right, so it does look like you have a few questions in the Q&A if you want to jump over to the Q&A box.
Okay, thanks. Okay, so for Saxi, so the loss arrow we used, okay, we want to show here. Okay, here. So the loss function, so for the first stage, the text to names part, it's cross entropy loss because we say it's basically the multi-class classification. So for this one, it's cross entropy loss. Because we say for this texture description, we in the data set we have the ground truth motion, so we know the ground truth motion in our data set, like the length of it. So we can just use that as the ground truth length and use that for training the model using cross entropy loss. And for this part, the text to motion, the loss function we used for the autoencoder, it's basically the reconstruction loss between the input and output. And we have some losses at the middle, try to enforce the sleepy code to be sparse. So we have the L1 regularization, and also we have some loss to enforce the consecutive sleepy codes to be close. Basically three loss terms. And for this part, we only have three losses. The first one is the reconstruction loss between this output sleepy code and the input sleepy code, and also the reconstruction between the motions here and also the input motion. So, and the third one is the KL divergence loss between this normal distribution and this normal distribution here. So there are three loss function here. Okay. And for Ali, So does it make any difference using a transformer-based language model such as BERT? So we do use BERT as our text encoder, but I'm not sure if I did something wrong, but it does not make a large difference. I feel like BERT in our task is okay, it's like a heavy model, but as following, I know many people are trying to address this problem using diffusion model for text to motion generation, and most of them they are using like clip text encoder and or BERT that do have some improvement in the performance. So.